Good morning. Welcome to Krishna's class. Today we look at the following problem. We have already seen that T belongs to L. It's a linear transformation on RK. Then for any Lebesgue measurable set, E is equal. We have T measure of TE equal to delta T to what is delta T? Delta T is scalar. Let us work it out. So what is delta? Now what we prove is that you know that given T belonging to K, sorry, L is a linear transformation of RK, there exists a matrix. Let matrix representation of T with respect to a basis. RK. Then we prove that delta T determinant of the matrix of T. Now you see that this matrix is an invariant. Sorry, not the matrix, that the matrix representation of T depends on the basis. On the other hand, determinant of T is an invariant. That means it is the same for determinant of T, the matrix T, and hence that is, it does not depend on the choice of the basis. Now, the reason is clear. If B1 and B2 are two bases for RK, and TB1 and TB2 are the matrix representations. With respect to B1 and B2, then we have, there exists an invertible matrix A such that TB1 is equal to and then consequently you see that if you take the determinant TB1 equal to and you see these are scalars, therefore this is equal to determinant of T2. So you see that the determinant does not really depend on the determinant of the matrix representing T does not really depend on the matrix representation of T, because there are several matrix representations, infinitely many matrix representations possible, and this is the connection between them, and this remains an invariant, and that is why we designated this. It is often written as determinant of T. That means these matrices that represent the same linear transformation under different bases are what are called similar matrices. Okay, therefore, so That means they are connected by this type of a relation. And they have the same determinant. Okay. So, since the determinant of does not depend on the choice of the basis, we designate it by determinant. Instead of putting the matrices, we simply write determinant of it. Okay. Now, what we assert now, this is a multiplying factor or a scaling factor for the measure induced. Okay, that's delta t. Delta t is a scaling factor, or in the change of measure represented by. See, you have what was the notation I have used? I have used say, so E belonging to M. You have measure of E, Lebesgue measure of. Then you take T, that is the image of T, E under T. This also belongs to M. And then you have the measure of. The question that we ask is, how measure of T is related to measure of E. And this is the one that we proved earlier, that this is equal to this is what we have proved earlier, that this is equal to so this is some number, some non-negative number associated with it. Okay, because delta T is greater than or equal to 0. That depends only on T and not on anything else. This factor does not depend on delta T, does not depend on that's a beautiful result. So what we want to this delta T is in fact, now determinant of T may be positive or negative, okay, or even 0. This is going to be, this factor is 0. Okay. Now let us prove this. Okay. So we start with the analysis. So that's the background. Now you take R. Let be the standard basis. It is easy to work with the standard basis. That means where EI equal to delta I1, delta I2, everyone knows. Okay. Now, how to get the matrix of T? So, let T be from Rk to then Tej equal to sigma I equal to 1 to k alpha ij Pm for j equal to k. The usual matrix representation. Then is given by the matrix this is standard. It's a standard result. How to get the matrix representation with respect to a basis. Okay. Now this is, of course, we designate by alpha. So this is a k by k matrix that you have. Okay. So I runs over the rows and j corresponds to the columns. Okay. So this is what you have. This is the matrix representation. That is T. So we show that delta T equal to determinant of the matrix alpha ij, which is equal to now you see that this is, of course, you see that I said this determinant is an invariant. Determinant of this determinant is an invariant, that is, it is invariant under the change of a basis. Now, how do we prove this? So, we shall designate this by 1 and this by 2. What is by 2? It's the second. See, one of the theorems that we use here is that if A is an invertible, it can be transformed to the identity matrix. The identity matrix I through a sequence of row operations. This we usually use in solving equations. Okay. So what is the consequence? I mean, there are 3 types of row operations that we use. Consequently, what we have is I is equal to, that is identity matrix, is equal to so 3 row operations are, there may be a finitely many, a finite sequence of it's a finite sequence of row operations. So let me write this as R1, something like we first apply R1 to what's where we start with A, then we apply R2, then we apply R3, R, where R1, R2, R3 representing row operations. Therefore, what you get consequently, which implies A is equal to, see that inverse operating over I, which is equal to, the inversion formula. So it is R1 inverse, R2 inverse, it's operating. Therefore, from this, what do you get? You get the following, which in turn implies determinant of A equal to determinant of R1 inverse, R2 inverse, Rn inverse I, this one, which is equal to determinant of into determinant of I, which is equal to 1, which is equal to determinant of inverse. Therefore, the problem is, once you get these basic operations which transforms into I and then compute their inverses and the corresponding determinants, we get the determinant. Okay, so this relation we have. Okay, therefore, we observe the following. The row operations correspond to 3 times of the first one is this is type 1. PE1 is a permutation of that is the first one. The matrix of T then correspond to the interchange of rows So what you have is you have T1, T2. So you have the matrix for T with respect to E1, E2, Ek. We want to find out the matrix of T with respect to the basis E1, E2, Ek. So what happens is T Ei will go to some Ej. Okay, or in other words, you are just permuting this. The operation is T Ei goes to some Ej. So T is then you can consider this as a map on E1, E2, Ek, which simply permutes this. Okay, then what happens? What is the corresponding matrix? Then you see that T with respect to B. B is the standard basis, is a row permutation of identity matrix. For such a T, determinant of T equal to 1. Determinant of T is equal to 1. Simply, or modulus of determinant of T is equal to 1. Okay. The second type is the following. Type 2 is multiplying a single row by type 2 okay, I'll give an example here. This is better. So let us take A to B. A2. Now we want to transform this into interchange of the first row with the second row. We want to transform this into A21, A22, A11, A1. What do we do? Simply get this. Now note that A21 just multiply this. This is A21, A22. So the corresponding row operation is represented by multiplication by this. Now you see that the determinant of this transformation is equal to -1, which is therefore the absolute value of determinant of this transformation is equal to 1. That's what I have said. So if you take a 3 by 3 matrix and interchange the first row and the third row, then what you do is you interchange the corresponding rows of the identity matrix. So you get a new matrix and multiply by it. What will be the effect? Okay, the row will be interchanged. But you see that the determinant just changes the determinant of the multiplying matrix is essentially equal to -1. Okay, therefore the absolute value of that is equal. So that's what I said. So now we take the second type is we have TE1 equal to alpha and TEI equal to EI for I equal to 1 second. Okay. Now you see that if this is multiplying the I'll write it this way. It's going to be multiplying the jth row by alpha I not equal to j. Okay. Then what happens? You are taking the matrix, then now this is the jth row that you are taking. Jth row you multiply by alpha 0 and then all others as usual. So you take the identity matrix, take the jth row and multiply by this alpha. Okay. Then the effect of this is this. For example, you look at this one. 1 0 0 0 alpha 0 0 0 1. Take this and multiply by say A11, A12, A13, A21, A22, A23, A31, A32. What is the change that takes place? You see that this will go as it is. Now what happens to this? Multiplication would give you alpha times A21, alpha times A22, alpha times A23 and A31, A32, A33. So what is happening? The second row is now multiplied by alpha. That is the effect of this transformation. Okay. So in that case what happens? The corresponding determinant is equal to is then equal to simply alpha. Right? Now the third type of transformation is these are the elementary transformations that we come. The third operation is this. TE1 equal to E1 plus E2. It's a typical one. TEI EI I equal to 2, etc. That means the first element of the basis is transformed into the sum of the two, the vectors E1 and E2. All others are left as it is. This is a transformation. Now, in general, it could be something like, you take the kth row, k1th row, and you take the say ith row and take the jth row and add one to the other. That can happen. So, in this case, what happens? So, you have this one. Therefore, you have TE1 equal to E1 plus E2, TE2 equal to E2, TEK. Then the matrix of T is equal to this. What is it? The first one, then you have and so on. The remaining things remain the same as it is. This is the matrix representation. You see the change here. The second row is changed into, instead of 1, 0, 1, you have 1, 1. That is the change that it undergoes. You can easily work it out. Now, what happens to the matrix then? The determinant of T is now you can look at an example. What does this do? Suppose you use this matrix 1, 0, 0, 1, 1, 0, 0, 0, 1 and multiply, say alpha 1, 1, alpha 1, 2, what do you get? You get this transforms into the following matrix. What is it? The first row remains the same. Alpha 1, 1, alpha 1, 2, alpha. The second one is going to be alpha 1, 1 plus alpha 2, 1. Alpha 1, 2 plus alpha 2, 2. Then the third one is going to be alpha 1, 3 third one remains the same. Alpha 3, 1, alpha 3, 2, alpha. So the effect of this operation is essentially take the first row, add the second row to it and represent it as the second row. This is the operation. Okay. Now, if you want to take the ith row and the jth row and add one to the other, you have to make the corresponding change in this map. Okay. In any case, what you observe is that the determinant of the corresponding t is equal to 1. Okay. So that's easy to understand. These are the three types of operations. Because if you recall, how do we transform a matrix to the identity matrix? Okay. Let me just take an example. Work it. Nice to see this example. -2, 4, 5, -4. Suppose this is the matrix. Now we want to transform this to, note that this is invertible. Now let us systematically do this. So how do we do this? We'll take the -2, 4, 5, -14 and then bring 1 here. To bring 1 here, what you do? Take the first row and multiply by half. Okay. First row. Okay. That will lead to, what is that? 1, 2, 5, -14. As it is. They don't change at all. There may be a sign change that we'll have to account for. I will do that as it is. So this means that this transformation. So you can write some P1 into 2, 4, 5, -14 equal to, you have a matrix multiplication. The matrix multiplication corresponds to the first row of R1. Okay. So start. So what do you get this into this equal to minus 2, this into this equal to what? You get 2, so this is equal to 1 1 0, and then this you take and this you multiply, so you get sorry, it should be okay. This is what you get, right? This is the matrix matrix. So you are effectively multiplying this matrix and you call this sum. So this is what you get as the matrix of T. Similarly, what is the next operation? The next operation is you multiply by okay. How to go from here? From here, what you do is you subtract 5 times this. Okay. Then what happens? You'll get 0 here. Okay. All right. So this you transform to 1 minus 2, subtract 5 times that. So minus 2, 5 times that is 0. So this will become 24. Oh, okay. Right? Now what do you do? The third operation would be to transform this into multiply the second row by 1 by 24. So let me, to get the numbers smaller, I'll put minus here. So you get this one. Okay. This goes to minus 14. Plus 14. Take. So this is equal to minus 14. This is what you get. Now you take this and then do the operation. To do this operation, then what happens is 1, 2, 5, 14. So you have what you get as subtract this. Okay, you got 1, 2, 5 minus 14. 1 to 5 minus 14. Okay, let me work with this plus 14. Get the things smaller. Get this one. Now, what do you get? 14. Now you change this, so you get 0, 14 minus, 14 minus 10. So this is going to be 4. Okay, that is the next step. And the next transformation is multiply this by 1 by 4. Okay, so 1 by 4 R. Okay, then this is actually R2 minus 5 times R1. That will give you what? 1 minus 2, 0, 1. Now this goes to, you subtract from R1, or add to it 2 times R2. That will give you so each of the operations correspond to a scalar multiplication, change of base, etc., etc. So essentially, to see that the entire operation can be written as sort of multiple of these operations. Not, you cannot say in some order. It depends on the given matrix, or it depends on the way you do. So essentially, you end up with the following. That is A equal to, or I equal to, you first apply T1, then apply T2, these are all row operations. Okay, therefore, what you end up with? You end up with determinant of I 1 equal to, okay, or I A equal to this. So we multiply by Tn inverse, Tn minus 1 inverse, T1 inverse into I, into A. Therefore, you get what? Determinant of A equal to determinant of Okay, so these are the operations. On the other hand, you have the transformation working. Okay, then you eventually get there, as I have done in the beginning, how these transformations connect. Okay, so you get eventually determinant of A equal to. Okay, how do we get that? So let us take the case of, say, T equal to T1, T2. Both are elementary row operations of some kind. And then you see T is it's an invertible matrix. Then what you get? You get T of, say, E equal to T1, T2. Therefore, what do you get? Measure of T equal to measure of T. And what is that? That's equal to delta T1 into, so this is equal to delta T, measure of E equal to this. This is equal to delta T1 into measure of E, which is equal to delta T1 into measure of T1 is delta T2 into measure of, which implies delta T so in general, suppose then you have delta T equal to delta T1, delta T2, delta T. So you see the measure of E is different from 0, therefore you can see. So for any E, delta T into ME equal to this one. That's where you get this result. And then extending this for this cases, you get this. These are all elementary operations. So therefore, it is sufficient to establish what are the matrices for the corresponding elementary operations. Okay. So for type 1, what about type 1? T has exactly 1 in each row. And each column. This corresponds to the permutation of E1, E2, etc. En. Okay. And 0, 0 elsewhere. We are talking about the matrix of acceleration. Okay, that is the matrix one. Okay, then what happens? Then delta t for such a t is equal to plus or minus. Okay, so what we have is determinant of t is then equal to plus or minus. Okay, so what is the consequence? Now TQ TE equal to del measure of TE equal to what? Delta T into measure of, okay, which implies measure of, sorry, delta T is equal to okay, for that this is true and this is equal to 1 in this case. What happens in this case? You are taking, okay, how do we prove this? Take the basic units of this. Let Q be the cube consisting of say K with, this is the unit cube that you are considering. Then we have then for T belonging to the first type, type 1, we have determinant of T equal to plus or minus 1. That's what we have shown there. And you have TQ is essentially equal to Q. This is the crucial. Because what you are doing is in R2, if you are taking the unit cube, unit square. This is the square that we are taking. Now use the transformation of interchange of E1 to E2. That means E1, E2, see, here E1 goes to, okay, suppose X is equal to then Tx is equal to psi 1 Te1 psi 2 Te2. What is that? That's equal to psi 2 Te1 is E2. So psi 1 E1 plus psi 1 E2 plus psi 2 E. Okay. Now you can easily see that what is this operation? This operation is just suppose you take this point and then you are flipping it across, and this point is mapped to this point. Okay, this is coordinates, this coordinate. Okay, so that's the transformation that you get there, right? And then what is the effect? The entire half, this half of the box is mapped over to that is mapped over. Okay, so what is the effect? In turn, the measure does not change. So I draw a bigger picture to give a feeling. In the case of R2, suppose you take the key. Okay, so this is, you take a point whose coordinates are psi1, psi2. So this is the vector E1, this is the vector E2. So this point is essentially psi1, E1, T2. Now what happens to this point under T? Under T, this is mapped to the point psi2, psi1. Okay, that's what you have seen. This is the map that goes. So essentially, you have taken an arbitrary point in the lower triangle, goes to an arbitrary, leads to a corresponding point in upper triangle. So entire lower triangle gets mapped to the upper triangle and vice versa. So what happens? This is your cube. Okay. So under this transformation, the volume does not change, or volume or area does not change. That is what you understand. Okay. So this is the picture that you get. Right. So this is your cube. This whole thing is what is called here. Right. Type 2. What is the geometry for type 2? Type 2 is E1 equal to alpha E1, TEI equal to EI, or I equal to 1, 2, 3, etc. This is type. Okay. Then what you are doing is the following. The picture is in R2. If you take, what happens to Q? So this is your Q. So any point, the first coordinate gets changed to alpha E1. Okay. So you get E1 goes to alpha E1. So this is stretched. And all of this remain the same. Okay. So the area is expanded. In fact, this one is stretched to this area. So what happens is the measure of TQ in this case is alpha times measure of T. What does it mean? This means delta T equal to the third one. Let us take. type 3. Okay. Now let us analyze this. Consider Q. Where Q consists of all the set of points that's the box. So in the case you have the Q. Okay. PQ, what happens to TQ? TQ is E1 to E2, E1 to E1 plus E2. So this is E1 to etc. This is your T transaction. Okay. Then what happens? Then TQ consists of all psi1 and 0 this is the transformation. So in short, let us see what happens in R2. Take R2. This is your now the first transformation is E1 is changed to, so you have this is the property of T. What happens? Okay. So let S1 be the set of points in TQ such that So what you get would be this is the transformation. This is T. Okay. So this part, this is your S1 and this is your, okay. Therefore, what do you get? Minus E2 equal to Q and S1 intersection S2 minus E2 equal to empty. This is what you get. So S1 union S2 minus this is not S2. Yeah, S2 minus E2 is this portion. This is S2 minus E2. This is S2 minus E2. Okay. Now S1 union S2 minus E2 equal to Q. S1 intersection. Now the intersection of these two is empty. That's what you get. Therefore, delta T equal to measure of which is equal to measure of these two, and that is equal to measure of Q, which is equal to 1. Okay. Therefore, equal to, what does it equal? Therefore, what do you get now? So you get delta of T. Suppose T equal to T1 Tn, then these are all elementary operations. Delta T equal to n, and each one is equal to modulus of determinant of T. So this is equal to this is equal to so that is what you get. Okay, so that completes the proof of the theorem. So the strategy is to break up the linear transformation into the product of elementary transformations. And for elementary transformations, we have the result. From that, we conclude for the case of the given transformation. Thank you very much.